Hi, I'm Professor Afshar at Glendale Community College. This is Physics 101, Lecture 12. In this lecture, we'll discuss projectile motion. This topic is covered in Chapter 4 of our textbook by Surway and Jewett. Before discussing projectile motion, we need to review some basic concepts. First, recall that when discussing two-dimensional motion, we must separate the motion into x and y components. This is referred to as decomposition of motion, an idea that dates back to Galileo, who discovered that the motion of a ball rolling off of a table can be analyzed by analyzing its velocity and acceleration in the x direction separately from its velocity and acceleration in the y direction. As a result of Galileo's decomposition of motion idea, going forward, when we discuss two-dimensional motion, we must separate all of the motion variables, in particular position, velocity, and acceleration, into separate x and y components. What this means is that going forward, we're going to talk about the position vector having two components, x and y, the velocity vector having two components, vx and vy, and the acceleration vector also having two components, a sub x and a sub y. The last item that we need to review is the kinematic equations. Recall that we derived the kinematic equations in Chapter 2. There we found that by integration we can obtain two equations labeled as equation 1 and equation 2 here, which relate the final position of an object and the final velocity of that object to things like time, acceleration, initial velocity, and initial position. By combining equations 1 and 2 with some algebra, we derived equation 3 and equation 4. These equations are extremely powerful because they allow us to analyze the motion of any object that has a constant acceleration in the x direction or in the y direction. These equations were limited to one-dimensional motion, so motion had to be either horizontal or vertical. Our goal in this chapter is to generalize these equations to two-dimensional motion. As it turns out, the kinematic equations in 2D are not very different from the kinematic equations in 1D. Following Galileo's prescription for decomposing motion into x and y components, we simply write two sets of equations, one set for the x motion and an identical set for the y motion. Shown here on the left are the kinematic equations that you're familiar with. These describe the x component of the motion, whereas on the right, in blue, we have the equations that dictate the y component of motion. Notice that the equations on the left and the equations on the right are essentially identical. Mathematically, they are identical. However, the variable names have been changed somewhat. On the left, we have the initial x-coordinate and the final x-coordinate, whereas on the right, we have the initial y-coordinate and the final y-coordinate. On the left, we have the initial velocity in the x direction and the final velocity in the x direction. On the right, again, we have the initial velocity, but in the y direction, and the final velocity in the y direction. On the left, we have acceleration in the x direction, whereas on the right, we have acceleration in the y direction. So we're not really going to rederive all of these equations. The mathematical derivation of these equations was covered in Chapter 2. These are essentially the same equations. However, we relabeled some of our variables so that now they can be separately applied to the x direction and the y direction. There is one caveat for using these equations. The acceleration of the object in motion must be constant. And this was the same condition that we had in Chapter 2. In deriving these equations, we assumed that the acceleration was constant, and that fact has not changed here. There are many examples of two-dimensional motion. However, for us in this class, there are two examples that are extremely important. The two examples of two-dimensional motion that we're most interested in are projectile motion, which we will discuss now, and circular motion, which we'll discuss in our next lecture. What is projectile motion? Projectile motion is first and foremost two-dimensional motion, and it is motion that is subject only to gravity. So when an object is moving in two dimensions and the only force acting on it is the force of gravity, we say that we have projectile motion. We have already discussed free fall as an example of motion where only gravity acts. If we want, you can think of free fall motion as a special case of projectile motion, as sort of a boring example of projectile motion, because everything is happening in only one direction, but more generally, projectile motion can happen in two dimensions. There are many examples of projectile motion. An artillery shell fired out of a cannon is undergoing projectile motion. A basketball free throw is an example of projectile motion. A person simply jumping forward is executing projectile motion. A dart thrown at a dartboard, or even, as I was saying, a rock in free fall, these are all examples of projectile motion. Now, to be precise, in many of these cases, there is a secondary force, the force of air resistance, that can slow down the basketball or slow down the person in the long jump. However, it turns out in these examples and many other ones like them, the force of air resistance is quite small. In fact, it's quite negligible when compared to the force of gravity. So although technically many of these examples are not projectile motion, we will treat them as projectile motion because in many cases the effect or influence of air resistance is quite small, small enough to be negligible. Our goal is to use our two-dimensional kinematic equations to analyze projectile motion. As before, we're going to separate the motion into x and y components. We're going to talk about x acceleration and y acceleration separately, x velocity and y velocity separately. And we're also going to remember that acceleration in the y direction is going to be 9.8 meters per second squared. More precisely, acceleration in the y direction is going to be minus 9.8 meters per second squared, assuming that we're using a standard xy coordinate system where up is positive. As we've discussed before, it is possible to adopt a coordinate system where the down direction is the positive direction. In that case, you would substitute plus 9.8 into the kinematic equations. We are treating the x and y motion separately, so in addition to specifying the y acceleration, we must also specify the x acceleration. Since we're interested specifically in projectile motion, and since in that case gravity is the only force acting on the object, the x acceleration is going to be 0. In other words, no forces are pushing or pulling the object in the x direction, so the object has no reason to speed up or slow down. Its acceleration in the x direction will be 0, however, its speed or velocity in the y direction will be changing because of the force of gravity. Notice that both of these accelerations are constant, and therefore we can use the kinematic equations. So our goal for the remainder of this lecture is essentially to take the kinematic equations in 2D, adapt them to projectile motion, and then use them to answer interesting questions about projectile motion, like how far will the projectile go, or how high the projectile will fly. Here, once again, are the kinematic equations in 2 dimensions. On the left, we have 4 equations that describe the x motion, whereas on the right, we have 4 equations that describe the y motion. Our goal is to specialize these 8 equations to specifically projectile motion. Remember that for the case of projectile motion, acceleration in the x direction is 0, and acceleration in the y direction is minus 9.8. So for every instance of a sub x, here and here and here, we substitute 0. And for every instance of a sub y, here and here and here, we substitute minus 9.8. In some cases, you'll see that the minus 9.8 meters per second squared is sometimes written simply as minus g, where g stands for the gravitational acceleration of 9.8 meters per second squared. As a result of these substitutions, our 8 equations simplify to essentially 6 equations. Notice that some of these equations become redundant. For example, equation 1 and equation 2 here are identical. Similarly, equation 3 and equation 4 here are identical. So the result of setting the x acceleration equal to 0 is that some of these equations become redundant. The end result is a set of 6 equations that tell us precisely how a projectile will reach its maximum height, how it will reach its range, and it also allows us to calculate things like the time of flight. Here's a typical practice problem involving projectile motion. A cannonball of mass 35 kilograms is fired with an initial speed of 50 meters per second at an angle of 45 degrees with respect to the ground. Given this information, find the time of flight. The time of flight is the total time that the projectile is in flight from when it is fired from the cannon to when it lands. Also, find the range of the projectile. The range of the projectile is the total horizontal distance that is traveled by the projectile, or the cannonball in this case. We also want to find the maximum height of the projectile. That's relatively self-explanatory. It's the maximum vertical distance from the ground. The picture shown here is not exactly to scale. In problems of this sort, we often ignore the size of the cannon or the person that is throwing the ball relative to the range and maximum height of the motion. So we're going to ignore the initial height of this projectile and assume, at least in this example, that the projectile is starting on the ground. Our goal is to answer these 3 questions using the kinematic equations specialized to the case of projectile motion. Here on the right, you see the 6 kinematic equations that have been specialized to the case of projectile motion. Recall that for projectile motion, the acceleration in the x direction is 0, so you don't see a sub x anywhere in these equations. And in the case of y acceleration, that acceleration is minus 9.8. We've written that as minus g in all of these equations here. Our first task is to figure out the time of flight. In order to answer a question like this, you have to take your time and systematically go through this set of equations and see which equation is suitable to the task. This is something that requires a lot of practice. To begin with, you may want to memorize these equations or at least have them near you so that you can reference them when you're working on your homework, for example. Once you have these equations memorized or you have them somewhere written down, you can systematically go through them and see which one is suitable for finding the time of flight. We obviously want an equation that involves t in it. So immediately I would say that equation 2 is ruled out because there is no time in it. I would also say that equation 6 is ruled out for answering this equation because, again, there is no time in it. Equation 1 does have time in it. That seems attractive. I also know what x initial is, and with a little bit of work, we can probably figure out what Vix is. Unfortunately, I don't know what the final position of the projectile will be when it hits the ground. Therefore, I'm going to rule out equation 1 as well. Equation 1 has 2 unknowns in it, t and xf, so it's not really suitable for solving for t. Equation 3 turns out to be a good equation. I know that the projectile starts on the ground, so I can set this equal to 0. And I also know that the projectile eventually lands on the ground, so I can set y final also equal to 0. I know what g is. G is simply 9.8. And I also know what the initial component of velocity in the y direction is. In the y direction, we can say VIY is simply VI times sine of theta. Remember, here we're talking about the y component of the velocity vector. The initial speed that is given to us here, 50 meters per second, is really v initial. It's the magnitude of the velocity vector initially, and this velocity vector initially points at 45 degrees. And so if we're interested in the y component of that initial velocity, we must do a little bit of trigonometry and calculate the y component here. So this is VIY. As you can see, this length of the triangle is opposite to the angle of interest. And with a little bit of geometry, you can convince yourself that VIY should be VI sine theta. And theta, of course, is given to us as 45 degrees. So the end result is that equation 3 is actually a very good equation, because the only unknown in that equation is time. Everything else can be figured out relatively easily. At this point, you need to plug in numbers into this equation, and you need to do some algebra, possibly involving the quadratic formula, and solve for time. When you do that, you'll see that equation 3 implies that time, the time of flight, is 7.215 seconds. In other words, the cannonball is going to be up in the air for about 7 seconds before it lands on the ground. The second part of the problem asks for the range of the projectile. In other words, we want to know how far the projectile goes horizontally. We want to essentially know what x final is for this projectile. So once again, we play the same game. We go through our list of equations to see which ones are suitable and which ones aren't. I can immediately tell you that equation 3, equation 4, 5, and 6 are not suitable for answering this question. What we're really interested in is essentially knowing what x final is, right? Remember that x final is essentially the horizontal distance that this projectile will travel. X initial can be described as 0. So if we know x final, we essentially know the range of the projectile. Equations 3, 4, 5, and 6 are not suitable because none of them involve x final. Equation 2 also does not involve x final, so really the choice is quite simple. We must use equation 1 to answer this question. I know what x initial is. I'm going to plug in 0 for that. I know what v initial in the x direction is. This is going to be v initial times cosine of theta. Before we were talking about VIY, now we're talking about VIX. In the x direction, we have to use the cosine of the angle. In the y direction, we have to use the sine of the angle. Once again, VI is given to us, that's 50. Theta is given to us as 45 degrees. And we know what t is. T is our answer from part A of this problem. This is going to be 7.215 seconds, approximately. So we have everything except x final, which is the thing we're interested in. At this point, plug these numbers into your calculator, and you will find that x final, or the range of the projectile, is going to be approximately 255 meters. Part C of this problem asks for the maximum height of the projectile. This turns out to be the trickiest of these three. When the projectile reaches its maximum height, in some sense, it hasn't really finished its motion. There are several approaches that we can take to answering this question. For example, if we know that the total time of flight is approximately 7 seconds, we can surmise that it must reach its maximum height at exactly half this time. And that would be true for a simple problem like this. Once we have the time of flight, we can essentially solve for y sub f, and that would be the maximum height. So we can imagine the projectile starting on the ground, and the final velocity or the final coordinate could refer to its coordinate or velocity at its apex, at the highest point. And so knowing the time, we can find y final in that way. However, a slightly more clever strategy is to use equation 6. For this particular problem, we could recognize that when the projectile reaches its maximum height, it is no longer going up. If it's no longer going up, then its final velocity in the y direction must be 0. So to answer question C without relying on parts A and B, we can simply use equation 6. We can say that v final in the y direction is 0. It has to be 0 because we're talking about the maximum height. If the object still had some y velocity at its apex, then it would still be going up. That point would not be the maximum height. So we're going to set this equal to 0. We know what v initial in the y direction is. It is vi sine of theta. Don't forget to square the whole thing. We know what g is. That's 9.8. We know y initial is 0. So the only thing we don't know in this equation is y final. And y final is exactly what we want. It is the maximum height of the projectile. So plug the numbers in and solve for yf. With a little bit of algebra, you should be able to find that the maximum height of this projectile is 63.776 meters. Let's review some important properties of projectile motion. We're talking about an object that has some initial velocity we're going to call vi. The object has some mass, although the mass of the object ends up not being important in answering typical projectile motion problems. The initial velocity will have some x component and it will have some y component. You can solve for those using a little bit of geometry. You can recognize that whichever direction the velocity vector has, it's going to have an x component and a y component. The x and y components will essentially be the adjacent leg and the opposite leg of a triangle. The initial angle with which the projectile is fired is usually provided to us, so once we know theta, we can figure out vix easily by saying that that must be equal to the initial velocity times cosine of theta, and we can figure out viy relatively easily. We can say that's equal to vi times sine of theta. It turns out that the motion is parabolic. This is something that we haven't really proven. However, if you look at the kinematic equations, you'll see that most of them are quadratic equations or second order polynomials, and these second order polynomials often describe parabolas. One of the questions that you often get is the maximum height, or essentially the y coordinate of the projectile at its apex. Remember that when the projectile reaches the apex, its velocity will be horizontal, like so. Remember that the velocity is always tangent to the path that the object follows. At its maximum, the tangent is going to have a slope of 0. It will be a horizontal line. What this means is that at this point, the y component of velocity is 0. This is a useful fact because you can often use this fact to calculate what the maximum height must be. Also note that throughout the trajectory, v sub x is constant. V sub x is constant because the acceleration in the x direction is 0. When the acceleration is 0, the velocity doesn't change. Specifically, the x acceleration is 0, so the x velocity must be constant. Also, the motion is symmetric about the apex. In some sense, what's happening on the left of the apex is equal to what's happening on the right of the apex. This is not entirely true. It's true only for situations where the projectile essentially starts on the ground and ends on the ground. So the starting elevation and the ending elevation are equal. Soon we'll encounter examples where that's not true, but for simple cases like this, you could say that there is a symmetry from the left to the right of the apex. Here's a more challenging example of projectile motion. A cannonball is fired from a height of 50 meters at an angle of 30 degrees from the horizontal and with an initial speed of 10 meters per second. Find the time of flight. Notice this is not a symmetric example. So the cannonball begins at one elevation and then it ends at a totally different elevation. So essentially we're to begin with on top of a hill 50 meters up, and then we're going to fire this cannonball into a valley 50 meters below. We're interested in knowing the time of flight, which is the total time it takes for the cannonball to travel from its initial position to its final position on the ground. As usual, you should have the kinematic equations written down next to you or have them memorized. Remember that the 8 kinematic equations essentially reduce to 6 kinematic equations when we're discussing projectile motion. Also remember that the x acceleration is going to be 0 and the y acceleration is going to be minus 9.8 or minus g. You need to go through your list of kinematic equations and see which ones are suitable for answering this question. Obviously, since we're interested in the time of flight, you want to choose an equation that involves t. As you're looking at your equations, you're probably noticing that you need to know things like the y component of velocity and the x component of velocity. Remember, we want to always decompose motion into separate components. For this particular problem, the y component of the initial velocity is 10 sine 30. 10 is v initial, so this number here is going to end up being v initial, and of course the 30 degrees is this 30 degrees that's given to us in the problem. 10 sine 30 gives us 5. This is the y component of the velocity. I'm calculating the y component of velocity because as I look through my list of kinematic equations, I realize that this equation here is the right equation for us. I like this equation because I know what y initial is. That's the starting point of the projectile. I also know what the final y coordinate is. I know what g is. That's of course 9.8, and v initial in the y direction is 5. So once we substitute numbers into this equation, we can solve for t. There is one subtlety here. You need to decide what kind of a coordinate system you want to choose. We're going to use a standard xy coordinate system where y is where the positive y points in the up direction. And we're going to choose our coordinate origin so that it lies on the ground. This is not a necessary choice. Some of you might be thinking, well, can we put the coordinate origin up on the hill where the cannon starts? And yes, you certainly can. That doesn't affect the final answer, but it does affect the intermediate steps. If we put the origin on the ground, then we find that y initial is 50 because our 0 is on the ground and initially the cannonball starts 50 meters off the ground. Our y final is going to be 0 because that's where the cannonball ends up, on the ground, and we're calling the ground the origin. G, of course, is 9.8. V initial in the y direction is 5. And now we have a quadratic equation that we can solve for t. Don't forget that when you use a quadratic formula to solve for an unknown, you often get two numbers, and you should really check both of those numbers. In this particular case, if you plug these numbers into your calculator and solve the quadratic formula, the two numbers that you'll get will be minus 2.7 and 3.7 seconds. Of these two equations, or these two solutions, we're going to reject the negative one, meaning that we can't have a projectile landing on the ground before it was fired, and we're going to say that the positive root, or the positive solution to the quadratic formula, is the correct answer. So the time of flight in this problem ends up being 3.745 seconds. And that's the end of this lecture. Thank you for your attention.